Good morning. All right, so we've got a couple more examples to finish up in 2.7, then we'll get into 2.8 today. Should be able to finish that up. That's my goal. If we have any examples left, then we'll finish them tomorrow. But I still do want to review for the test tomorrow also. And then again, that'll be posted Sunday night at midnight and then do Tuesday night at midnight. So that's our goal right now. So get through the rest of chapter 2, review for the test, and then the test will be posted early next week and due before spring break. All right. The other thing is the homework. I moved to Friday of this week, so it was initially due by midnight tonight, but I'm giving you a couple more days to get that done. But again, we should finish up all of 2.8 today, or at least enough to get you through the homework, but I'm giving you a couple more days to get that done. Okay? Any questions, comments, concerns before we get started today? All right. That's right. So test 2 is going to be from Sunday to Tuesday. So it'll be posted midnight Sunday night and due by 11:59 p.m. on Tuesday night. Okay. Yeah, Haley. So next week, starting on Sunday, due on Tuesday. Any other questions? Yeah, and just a reminder, spring break is next week, right? So Wednesday, Thursday, Friday, no classes any of those days next week. All right. So if we take a look at this one now, now we've got a composition of 3 different functions. So we have an f, a g, and an h function, and we want to compose them all. So we're looking for f of g of h. So the first thing I'm going to do here is I'm going to rewrite this as f of g of h of x. Okay, so just keep everything right in order, just like we would if it was just f of g or g of f. All right, now, remember, we always start with our inside function. So what's the inside function this time? Good. The h of x is our inside function. So what I'm going to do is I'm going to replace h of x with x plus 3 now. So now we're going to have f of g of x plus 3. Okay, so just figure out what's your innermost function and then replace that function with whatever the function actually is. Now we can work our way out. So what we want to do next is we want to find g of x plus 3. So what we do now is take that x plus 3, substitute it into the g function. So if I do that, what's that going to look like? Good. So we're raising x plus 3 to the 10th power, right? Because I'm substituting x plus 3 in place of the x. So we're looking for f of x plus 3 to the 10th power. Okay. Any questions about how I got that step? All right. And so then what we need to do is take what we've got in there and actually substitute it into the f function. Now notice the f this time has 2 different x's, so both of those are going to get replaced with an x plus 3 to the 10th power. So once we do that, it's going to look like this. X plus 3 to the 10th in the numerator over x plus 3 to the 10th and then plus 1. So again, I'm just taking that f function and both of those x's get replaced with an x plus 3 to the 10th power. I don't expect you to actually expand this out and simplify it or anything. There are no common factors that are going to cancel. Okay, so be real careful. A lot of people want to try to cancel out the x plus 3 to the 10th now, but because of that plus 1, those are not common factors. We can't cancel them out. Okay, so this right here would be our final answer this time. Any questions on that one now? Now, this one didn't ask us to find domain, but since we've talked about it on other problems, I want to talk about this one real quick. Where could we potentially have restrictions on the domain of this one? What do we have to look at? Good, the denominator, right? So since we have a fraction, we know the denominator can't be equal to 0. So we would have to say that x plus 3 to the 10th power plus 1 can't be equal to 0. Now, here's what I want you to think about. If I substitute values in for x in x plus 3, I raise them to the 10th power. What's going to always be true about those values when I raise them to the 10th power? They're going to be positive, right? Because if I take a negative value and raise it to an even power, it's going to become a positive value. The smallest possible value I could get out of that now is 0, right? Because I could put a -3 in there. I could get a 0 to the 10th, which is 0. But in every single case, I'm adding 1. So when I add the 1 to that, it automatically becomes a positive. So will any of that ever be equal to 0? Is there anything I could ever put in for x that would make this equal 0 now? No, right? So because this is undefined now, right, there are no values of x that would make that equal 0. We would say that our domain this time is just all real numbers, negative infinity to positive infinity. So even though we have a fraction, right, and we have an x in the denominator, there's nothing I could put in for that x that would actually make that denominator equal 0. So we still have all real numbers as our domain this time. Oh, and you would need to check the inside functions. I didn't really look at that, but x to the 10th and x plus 3, both of those inside functions have a domain of all real numbers. So we can just say that, yeah, the domain here should be all reals. Any questions on that one now? All right. Example 6. So this time we're given an f of x function, and we want to find two functions that we could compose to give us that original function now. Okay, so we're working backwards. We're looking for the two functions that if we found f of g, it would give us the function that they gave us there. Okay. So what do you think we could do here? How could we find those two functions? Okay, so let's start here. I know that f of g I could write as f of g of x, right? Okay. All right, exactly. That's what we're doing is we're trying to break it into two parts, right? So we just got to figure out what those two parts are going to be. So now what I'm looking at is the g of x is the inside function, right? So I want to start actually with my g of x function this time and think about what that could be if it's the inside function. So look at the fourth root of x plus 9. X plus 9 is what's on the inside, right? So I'm going to let that inside piece be x plus 9 here. Now the question is, well, what would f of x need to be so that I could substitute g into that function and end up with the fourth x plus 9? We're just going to use the fourth root of x. Good. So this is going to be the fourth root of x, because now if I actually simplify this, this becomes f of x plus 9. Then I would substitute that into the f function, which would give us the fourth root of x plus 9. So whenever you're looking for what two functions could you compose to give you an original function, look for the inside function first. Go ahead and define what that inside is, and then just think about what are we doing to that function. That's going to be the f or the outside function now. Okay. Now, the one thing we cannot do is use x as our inside function, okay, because then our outside function would just be the entire original function anyway. Okay, so make sure that you've got more than just an x as the g of x here. Any questions on that one now? Now, just so you know, right, there are multiple answers to this one. You could have actually said, well, what if g of x was equal to the square root of x plus 9? What would f of x need to be to give us the original function in that case? Square root of x, right? Because if you take the square root of a square root of x plus 9, remember that would give us a fourth root of x plus 9. That would also be a combination of functions that would work. So there's not just one answer here, right? You could have multiple values. Those are the two most common, right, that I would see. But just know that a lot of times, right, there's going to be multiple answers to a problem like this. Any questions on that one now? There's not, right? And so I would say for a problem like this, the reason we like to do this is for calculus purposes. You know, if you go on to calculus, this form right here is going to be the most useful for us, just because it's easier to do a lot of our processes with a linear function than to have to do it with two square root functions. Okay, so there's no most right answer. They're both completely mathematically correct, right? But when you get to calculus, this first one is probably the way you're going to want to break it down, just because it'll make that other process easier for us. You don't need to list all of them. But, you know, if you find one combination that works, that's all. Okay. Any other questions there? All right. So that's all we got for that section. Now we got 2.8. All right, so 2.8, one-to-one functions and their inverses. Okay, so we're going to start with what's the definition of a one-to-one function, and then we'll look at how do you find the inverse of a function that is one-to-one. All right, so a function with a domain of A is called one-to-one if no two elements of that domain have the same image. Okay, so if we look at our map here, right, we've got 4 goes to 10, 3 goes to 7, 2 goes to 4, 1 goes to 2. Okay, so in this case, every x value maps to exactly one y value. That's what makes this a one-to-one function. Over here now, the g function is still a function because every x goes to a y value, right? So we don't have an x going to two different y's. Every x goes to one y. But notice here that I have two different x values going to the same y value. If that happens, then this one is not one-to-one anymore. So every x has to go to a unique y value. If that's not the case, then it's not one-to-one anymore. Now, the way we can test if we have a graph of a function is we can use what we call the horizontal line test now. Okay, so remember, vertical line test tells us if it's a function at all. And now if we use the horizontal line test, we can actually pass a horizontal line over a function. If it touches more than one point, then it's no longer one-to-one. Okay, that's right. So x squared is an example of a function that would not be one-to-one because if you pass a vertical or a horizontal line over it, right, then it's going to touch more than one point. And so we would say that is not a one-to-one function. And again, the reason there is I have two different x values that map to the same y value for x squared. Any questions about what it means to be one-to-one now? Now, the reason this is important is when we get to inverse functions, only one-to-one functions have inverses that are also functions. Okay, so we can still find the inverse of things that aren't one-to-one, but those inverses won't be functions anymore. All right, so here we go. We want to determine, are each of these functions one-to-one? So the way I'm going to do this is I'm going to think about their graphs. Okay, so let's think about the graph of x to the third power, what it looks like, and then we'll decide, is it a one-to-one function? Does anybody remember what the x cubed graph looks like? Okay, so x cubed actually only increases. Okay, so if we're reading from left to right here, it's like a sideways S shape, and it goes through the origin, but it does like this, right? It's increasing, goes to the origin, and then it continues to increase like this. So that's what x cubed would look like. Now, if I use my horizontal line test here, is this a one-to-one function? Yeah, right? So if I pass a horizontal line over that curve, it's never going to touch more than 1 point. And so we can say that this one is one-to-one. Okay, so every x goes to a different y value now. Any questions about that one, why that one is one-to-one? Okay, and then here's the x squared that we kind of mentioned on the last slide. Let's actually look at the graph though. So we know x squared is a parabola. Vertex is at the origin. We got something like that. And in this case, if I use my horizontal line test, is this going to be one-to-one or not? It's not, right? Because a horizontal line would touch multiple points on that graph. And so we would say that this one is not one-to-one. And again, you could say like this x value here and this x value here have the exact same y value, and that's why it is not a one-to-one function anymore. Any questions on that one? All right. Not going to do that one. All right. Definition of an inverse function. Okay, so we're going to let f be a one-to-one function with a domain of a and a range of b. So domain, here's the set of all the values of x. Range is the set of all the values of y. Its inverse function, this is the notation we're going to use. So we read that as f inverse. It looks like a -1 as an exponent. Okay, it's read f inverse, has a domain of b and a range of a. And f inverse of y is equal to x implies that f of x is equal to y. Now, all you need to recognize here is that if the domain of the original function is a, the domain of our inverse function is b, and the range of our original function is b, then the range of our inverse is a. In other words, we're switching the domain and the range, or we're switching the x's and y's. Okay, so notice here, the f inverse of y is just switching the x and y values for the f of x equals y function. Okay. So that's really all you need to understand here is when you're finding an inverse function, you're switching the x and y values. You're switching the domain and the range. All right, so let's take a look at this now. So we're given 3 points, f of 1 equals 5, f of 3 equals 7, and f of 8 equals -10. We want to find f inverse of 5. So if we think about each of these points now, keep in mind that f of 1, that means that the x value here is 1, and it corresponds to a y value of 5. So if I'm switching x and y now, and I'm finding f inverse of 5, what should f inverse of 5 be equal to? 1, right? So it's just going to be equal to the x value that corresponds to that original point. Any questions about how I got that? Okay. So same thing now with f of 7, or sorry, f inverse of 7. This is our x, this is our y, and so if we're switching x and y now, what's f inverse of 7 going to be equal to? Positive 3. Good. Because our y value originally was 7, the x value was 3. We switch x and y, so now the x value becomes 7, the y value becomes 3. All right, and then finally we're looking for f inverse of negative 10. So again, I have this point up here where x is 8, y is negative 10. So f inverse of negative 10 should be what? Positive 8. Good. Any questions about how we found any of those values? All right, so that's how we do it if you're given specific points, right? All you got to do is switch the x and y values there, and that'll give you what we've got for those points. And now we're going to look at an overall function, right? So we're given f of x equals 3x minus 2. We want to find its inverse. All right, now, first things first, right? 3x minus 2 is what type of function? Linear, good. So if we have a linear function here, is that going to be 1 to 1? Yeah, right. So all linear functions, right, if I pass a horizontal line over it, it's only going to touch one point on that line. And so this is definitely 1 to 1. So we know it's going to have an inverse function now. So to find that inverse function, I'm going to change my f of x to a y first. So I'm just going to write this as y equals 3x minus 2. Now, remember, to find the inverse, we're switching x and y. So I'm literally going to switch my y's to x's and my x's to y's in that equation. So this is going to become x equals 3y minus 2. That's our first step. Switch x and y. Now we need to resolve that equation for y. So what could I do here to get y by itself? Add the 2. Good. So that's going to give us x plus 2 equals 3y. And then we would have to do what? Divide by 3. And just keep in mind that when we divide by 3 here, we're dividing every single term by 3. So that's going to give us y. And on the other side then, what's that going to leave us with? Okay, so keep in mind, right, I divided the x by 3 and the 2 by 3. Good, so it's going to be 1/3 x plus 2/3. So just make sure you're dividing both of those terms by 3 here. So we get 1/3 x plus 2/3 equals y. That is now our inverse function. So we just need to make sure we label it as an inverse function. So we would say that f inverse of x is equal to 1/3 x plus 2/3. Okay. So start with a y equals equation, right? Change your f of x to a y. switch the x and y values, and then resolve that equation for y, and whatever you get is going to be your inverse function now. Any questions on that one? You could write it as x over 3 plus 2/3, right? That's fine too. It's just I like it in this form because it's mx plus b, so we can easily see the y-intercept and the slope. But what you have there is not wrong. Any other questions there? All right. Let's take a look at this one now. So same thing, we want to find the inverse function of x to the fifth minus 3 over 2. All right, so what's our first step going to be here? So we're going to switch x and y, right? So if I rewrite this first as just y equals x to the fifth minus 3 over 2, swap your x and y. So x equals y to the fifth minus 3 over 2. And once we switch the x and y's, now what? Good. So if we want to solve for y here, what are we going to do first? Good. We can multiply both sides by the 2 to get rid of the fraction. So that's going to give us 2x equals y to the fifth minus 3. Okay. What's our next step? Add the 3 to both sides. So we'll have 2x plus 3 equals y to the fifth. All right, and then what do we have to do at that point? Good. We need a fifth root here to get rid of the fifth power, right? So I'm going to take the fifth root of both sides to cancel out that y to the fifth. So that's going to give us y equals the fifth root of 2x plus 3. And then just keep in mind, we always want to rewrite it as an inverse function now. So this would be f inverse of x is equal to the fifth root of 2x plus 3. That's our inverse function. And I didn't say this at the beginning, but x to the fifth minus 3 over 2, right? If you wanted to think of it as like 1/2 x to the fifth minus 3 halves, that's just going to be an x to the fifth function with an odd exponent. So that's going to look kind of like x cubed with a vertical shrink by a factor of a half and shifted down 3/2 units. But because it looks very similar to x cubed, it's still going to be a one-to-one function. Okay, so that's why we can even find an inverse for this one to begin with. Any questions on finding the inverse function? The middle step, can you tell me specifically where you're looking? Are you looking at right in here? Okay, so the first thing I saw was I have a fraction, so I'm trying to get rid of the 2 in the denominator. So I just multiply both sides by the 2 so that these 2's cancel each other out. So then once I do that, I'm left with just what's in the numerator, and then I have a 2x on the other side. Does that answer your question? Okay. Any other questions there? All right. Example 9. Okay, so now we want to find the inverse of this function, 2x plus 3 over x minus 1. And so again, I'm just going to go ahead and write this as y equals 2x plus 3 over x minus 1. And so what are we going to have to do first here? Good. Switch the x and y's. Now notice this time we've got two x's on the right-hand side. Both of those x's have to turn into y's. So this is going to become x equals 2y plus 3 over y minus 1. So every single x has to become a y in that case. All right, so now what do you think we're going to do next? Good. Let's get rid of the fraction, right? So I'm going to multiply both sides here by the y minus 1. So just like the last one, we multiplied by the 2 to get rid of the fraction. This time we're multiplying by y minus 1 because that's what's in the denominator. All right, so when I do that, that's going to give us x times y minus 1 equals, and then these factors cancel, so we're left with 2y plus 3. Any questions up to that point? All right, now keep in mind we're trying to solve for y here. What do you think we might want to do next? Okay, so we are eventually going to move the 3. Okay, now before I do that though, let's do this. I'm going to go ahead and distribute the x into this set of parentheses over here. Okay, so that's going to give us x times y, so xy, and then minus x. Okay, now notice we have two different terms that have a y in them, and I'm trying to get y by itself. So the next thing we want to do is actually get all of our y terms together and get everything else together on the opposite side. So it doesn't matter which way you move stuff, right? If you want to move the y's to the left, that's fine. If you want to move them to the right, that's fine. Okay, we get all the y terms together, get all the other terms on the other side. So what do you want to do next? Okay, so you want to move the 3 and the x plus y. All right, so we'll subtract 3 from both sides then. That'll give us xy minus x minus 3 equals 2y. And then we'll move the xy to the other side, which means we have to subtract it. So that'll give us negative x minus 3 equals 2y minus xy. Okay? All right, so now we've got all the y terms on one side, we've got everything else on the other side. If we're trying to get y by itself, what do you think we're going to have to do next? Now we can factor out the y. Good. So that's why we get all the y terms to one side, is now we have a common factor of y, and we can bring it out. So this leaves us with negative x minus 3 equals y times, if I factor out a y over here, what's going to be left? 2 minus x. Good. We have the 2 and then a negative x. So if I'm trying to get y by itself now, what would I have to do at that point? Good. Divide by what's in the parentheses there. So we're going to divide both sides by 2 minus x. Oops. That's going to give us y by itself on the right-hand side, and then negative x minus 3 over 2 minus x. And don't try to cancel any of that out, right? The addition, or yeah, the subtraction in the numerator and denominator prevents us from being able to cancel out anything because there's no common factors. Okay, so that would be our inverse. Now we can say f inverse of x equals negative x minus 3 over 2 minus x. All right, any questions on any of our steps for that one now? Okay. Now, the other thing I'm going to ask for on the test is the domain and range of this inverse function. Okay, so let's talk about that, even though it's not in the directions here. That's something I will ask for on the test. So how would we find the domain of that inverse now? Good. So we know the denominator can't be equal to 0, so I'm just going to take the 2 minus x and set it not equal to 0. Okay, so if we solve that now, what's our restriction going to be on the x value? What can x not be equal to? X can't be 2. Good. So I can just add x to both sides here. So 2 not equal to x. And then, of course, we'll always want to write this in interval notation, just like we have everything else. So this will be negative infinity to 2, and then 2 to infinity. That would be the domain. Perfect. All right. Now, this is the only time where I'm going to ask you for the range of something. And the reason is we know now that with an inverse function, the range of the inverse should be the same as the domain of the original function. So how would we find the range of this inverse function then? Okay, good. Take the domain of the original. How are we going to find the domain of the original function? Good. That denominator can't be equal to 0, right? So we had an x minus 1 in the denominator. Now what I'm going to do is I'm actually going to use right here, once we've switched the x and y values, since range technically is a y, I'm going to say that y minus 1 can't be equal to 0 now. But yeah, it's basically just taking the domain of the original function now. That should give us the range of our inverse. So what's our restriction on y going to be this time? One. Good. So y can't be equal to 1. So again, if we put that in interval notation, negative infinity to 1, and 1 to positive infinity. So on the test, if you look at my practice test, because I did post that also, you can see there's a problem similar to this, and that's exactly what I did. I found the inverse function and then found the domain and range. Domain just comes from the restrictions on the denominator of the inverse itself, and then the range is just the restrictions on the x values in the original function now. Any questions on that one? All right, last example. So now we want to sketch the graph of f of x equals square root of x minus 2. And then we're going to think about the inverse function of that once we've got the graph. All right, so first off, we can think about transformations here to get this graph. We know our parent function is going to be the square root of x. And then what type of transformation are we going to have this time? Good. It's going to shift to the right 2 units, right? Because a minus 2 grouped inside with the x is going to shift it to the right 2 units. So instead of starting from the origin this time, I'm going to start from positive 2 and have a point there. And then it's going to be that curve that opens up and to the right. Okay, so that's our square root of x minus 2 graph. All right, now what we want to do is we want to use that graph to sketch the graph of f inverse. So let's think about what we know about inverse functions now. Okay, so we know the domain and range are switched, okay, when we do this. So if I switch my x and y values for this graph, what would that graph look like? Where would it start? Let's start with that point. Okay, it's going to start on the y-axis instead of the x-axis. Right? And specifically, it's going to start at what point? 0, 2, right? So instead of starting at 2, 0, if we switch the x and y, now it's going to start at 0, 2. Okay? Now let's think about points beyond that. Okay, so we know in this case that graph's opening up and to the right like that. If I come out here, let's find another point that we might be able to plot. If I go with like 6, 3, 4, 5, 6, what's the y value going to be when x is equal to 6 there? Good, right? Because if I plug in 6, 6 minus 2 is 4, square root of 4 is 2, and so we know we're going to have a point at 6, 2, which means our inverse function now, if we're switching x's and y's, right, we know where there's a point at 0, 2, there's also going to be a point where then? 6, right? Because we're just switching the x and y's, which means we go over 2, up 3, 4, 5, 6. Sorry, that's going to be way up here. Okay, but now what's going to happen is we're going to get a graph that curves like this instead. And if you wanted to choose another point, right, you could. Obviously, I'm running out of room there to actually sketch it. Okay, but that's what that graph would actually look like now. So what I want to think about is I'm going to actually put both of these on the same coordinate grid, just in different colors. So we know the original graph looked like this. And then the graph of its inverse is that red graph there, right? That kind of looks like half of a parabola, right? How are those two things related graphically? So if you had to describe to somebody the relationship between those two, right, other than the x's and y's, okay, they're reflected over the line y equals x. Okay, so if I were to actually draw in a line with a slope of 1 that goes through the origin right here, okay, this line would be y equals x, right, because that would have a slope of 1, y-intercept of 0. All this is now is a reflection over that line y equals x. So whenever you're looking at inverse functions and you're thinking about their graphs, if you know the graph of the original, you can reflect it over the line y equals x, and that should give you the graph of its inverse. Okay. Now, the reason that's kind of important, right? Here's what I want you to think about. Let's look for the equation of f inverse. So I'm going to go back to my original here. Right? We had y equals the square root of x minus 2. What would I do first here to find the inverse? Okay, we're going to switch x and y, right? So this gives us x equals the square root of y minus 2. And now I've got to solve for y. So what would be our first step here to get y by itself? Square both sides, right? So I need to square both sides to get rid of that square root. So that's going to leave us with y minus 2 over here, x squared over here. Then what? Now we can add the 2. Good. So we're left with x squared plus 2 equals y. So our inverse function here is x squared plus 2. Now, what would x squared plus 2 actually look like? It would be a parabola, right? And it would be shifted up 2 units. So basically, we would end up with this graph, right? That looks like an entire parabola. The problem is we know that our range is restricted for the original graph. The range of this original function is only from 0 to infinity, which means the domain for this graph also has to be 0 to infinity. So we can't have both halves of that parabola. We can only have the right-hand side where x is greater than or equal to 0. And so that's why we only get that right-hand side of that parabola here. So looking at the function, you might think, oh yeah, it's just a parabola shifted up 2 units. But we have to remember that that domain is restricted, and that's why looking at the graph of the original function can kind of help us to see, yeah, I need to restrict that now to just be 0 to infinity, not the entire parabola. Okay? So again, if you're looking for an inverse, reflected over the line y equals x, and looking at the graphs a lot of times will help you to see what those restrictions are, just in case, right? It looks like your inverse should be an entire parabola, but it's really not, okay? So in this case, for that specific inverse function, they don't exist at all, right? Because in this case, if I'm literally taking an inverse of the square root of x minus 2, those values would not have existed for that function, so they can't exist for the inverse either. Right, so we know in general, right, the function x squared plus 2 would exist for all real numbers, okay, but because this is technically the inverse of a square root function now, it doesn't even exist on the left-hand side. Okay. Does that answer your question, Destry? Any other questions there? All right, so again, just remember, homework is due Friday by midnight. The test will be posted on Sunday at midnight and due Tuesday by midnight. And tomorrow we will spend the day actually going through the practice test. Okay, so if you want to take a look at that before tomorrow, just to see what questions you might have, but that's what we'll plan on doing tomorrow. Okay, let me know if you got any questions about anything. Have a great afternoon, and I will see you all tomorrow.